Welcome back. So, like I explained, I next want to talk about other notions of context sensitivity that go beyond call frames. Um, so the general idea behind context sensitivity, like I explained, is to increase precision by adding context information to data flow facts, right? And we have been seeing these calling contexts where that basically encode where data flow facts come from, right? So that's exactly what this call strings approach is about. By looking at this call stack, you know for each data flow fact where it originates from. So which call sites did we go through until we reach the current program point. But there's another concept called value contexts that does not actually attach call sites to data flow facts within these calling context strings. But it rather adds other information about values that the analysis computes with. And that tells you how the data flow facts were created and propagated through the program. So whereas this here, I would say is very structural information, right? So it basically tells you about the control flow along which you came in your program. This down here is more semantic information. It tells you what other analysis information that particular information that you're looking at was derived from. And that can also be very beneficial, as I will show you in the next few slides. One particular notion of these value contexts that I want to focus on first, but there are also others. But one particular notion is so-called object sensitivity and object-sensitive analysis. So the idea here, opposed to context sensitivity, or calling context sensitivity, I should say, is that we're not storing calling context strings, but we are rather storing information about different objects in the analysis. So in particular, we want to distinguish between different objects of the same type. Okay. And this can be relevant, for instance, for resolving method calls or also for resolving field accesses. And they are a special kind of value context because these objects, like you will see, typically they are represented by call sites in your program or by abstract representations of runtime objects. And they are therefore special analysis values. If you have an object insensitive analysis, on the other hand, it treats all objects of the same type as the same, but here we want to distinguish them. So to show you that in a bit more practical terms, let's take a look at the following example, actually. So here we have the same example program on both sides. And what is it doing? Basically, you are creating two different objects. And the field X of the first object of A, it's actually tainted with a secret value. Then we're leaking two different fields of A, one tainted, one not. And we are also leaking two different fields of another object B, both of which are not tainted, right? Because both objects are actually quite unrelated. But now first, let's actually not yet look at object sensitivity. Let's first look at again, a field-based and a field-sensitive analysis. And in a field-based analysis, such a field access or access path, you could also say, A.B, is approximated by capital A.B, if you remember, right? So we're basically losing the information about the concrete variable, but we're instead encoding this through the type, the declared type that this variable has, right? So this type here. And that's what we are propagating to the program, okay? And therefore, what we have here at the beginning is nothing is tainted, but then down here, A.X is tainted, okay? And what you now see is that here we have a leak because small a is of type capital A, and therefore, you know, we know that before the statement, this is actually tainted. So here we are leaking something. But the same is now also true for this statement because also B is of type, declared type A, right? And so we have tainted A.X here. And therefore, we now falsely assume that we could also have a leak at this program point. So that would be a false positive. That's why I've marked it red, okay? And that's why field-based analysis are also not that precise. Now, we could instead have a field-sensitive analysis where we model each such access path, by itself. So we keep variable information. That means here we are actually tainting small a.x, and it's kept that way. And now we know that we leak information here, but we don't leak it at b.x. So we have a more precise representation here. But this here is actually easier or simpler to model, right? So here we need to track individual variables that can actually give you a fairly large lattice depending on how many variables there are. And here you certainly have fewer declared types that are actually used for these variables. And therefore this will be a smaller lattice and you might get faster termination here in this case. Now the question is, could you, for instance, improve this analysis here by adding certain context information, and in particular by adding value contexts? And here, if you look at this example, then what's missing here, right? So here, we at both places we know that a.x is tainted, right? So a field x of some object of type A is tainted. That's what this information is telling us, and the same here. But we don't know which object we're talking about, right? We only know its type. And so now by adding object sensitivity, you can actually improve on such field-based analysis. So let's do that here. The idea is that we enhance the data flow facts with context information, but now as context, we're not using call sites, but now we're actually using allocation sites. And in particular, we are using points to sets, so sets of allocation sites as context values, okay? In this program, we have two allocation sites. Let's name them A1 and A2. And now we can do the following. So when we look at what is being tainted here, then using pointer analysis, we can actually figure out that the owner object here that is referenced by this variable A, it's actually created at A1, okay? And therefore the taint that is being created here, we could now model as such. So we still have the original taint information that we had previously, but now we are annotating this with such a string. Here it's a very trivial string. It only has length 1. But this is telling us that the owner object here is A1. So it's an object being created at that allocation site. Okay. Why does this help us? Now, if we propagate this further, then you will see the following. This here will go away. So we will not any longer have a false warning here. Why is that? Well, when we now get this piece of analysis information at this program statement, then we simply know that this relates only to objects allocated at A1. But now we can again use a points to analysis to compute the points to set of the owner object B in this case. And we will see that this points to set only contains A2. And this has an empty intersection with this points to set, right? So these points to sets, you could say, are incompatible. And therefore we know that this piece of information, this data flow fact, does not apply here to the statement. It's not relevant. It does relate to some tainted data, but that tainted data cannot be leaked here because we're talking about different owner objects. So this does give you more precise results, but obviously you also have more computations to do than in the regular field-based approach, right? Because you have to use these additional points to sets. They increase the size of your lattice. You can imagine you also have to use some a little less trivial merge operator again, like we saw in the core strings approach. And you also have to do these pointer analysis queries, all of which takes a bit of time. But this is being used, right? So some people use object sensitivity, and in some cases it does make sense, in particular if you're analyzing properties that strongly relate to these owner objects. So for instance, I know that in JavaScript, that's often very beneficial because JavaScript doesn't have very strong type information anyways, but often does make sense to particularly strongly reason about individual objects. In other languages, this approach might be less popular. But the general notion again is that in object-sensitive analysis, we track the owner objects within the data flow facts, like you just saw. And in a in an object-insensitive analysis, you don't do this. And like I said, object sensitivity, if it's a type of context sensitivity. So normally when people say it's a context sensitive analysis, they mean it's a calling context sensitive analysis. But actually this is a more broad notion, right? So object sensitivity is really a subclass of context sensitivity. And in this case, we use owner objects as context information. Now, again, you can have different context lengths here. So just as you have different context lengths for call strings based analysis, you can also have them for these object sensitive analysis as well. The difference is here that for these object sensitive analysis, the context is extended whenever you have a field dereference and not whenever you have a method call, because let me just show you the next example. I think that it will become quite clear. So let's assume we have the following little program. And here we again have two different call sites, okay? So we have an object A that we are creating, then we have another object that we are initializing this field a.f with, and then we're actually tainting that object's field x, okay? Now, you can have a so-called two object sensitive analysis here, which would tell you the following. It would tell you, okay, I've tainted a field a field x of an object of type B. Okay, that's what's happening here. And this object of type B was created at A2, but it's contained within an object that was created at A1. Okay, so that's what you would see here. And so that's telling you that you basically, it's telling you concrete objects associated with the two different elements of the access path that is being tainted here, you could say. Okay. If you have a one object sensitive analysis, it looks like this. So here again, we lose the left-hand side of the object string in this case, right? So it's not a calling context string anymore. It's rather an object string. So here we would only retain the information that we have tainted the field x of some object that was created at A2, but we don't know which object that was created here exactly it is, because we have lost this information that it was associated with A1. Now, sometimes that lost information may matter. Sometimes you may lose precision here. Sometimes you may not. That depends a lot on what the object structures in your program look like. In practice, the contexts are often not just allocation sites, but really actually points to sets. So that means basically you can have ambiguity here. So if I go back, right, so here I have a single string, but in practice you can have multiple ones, basically. You can have sets of such strings because, well, you can have ambiguities in your program, right, that is caused by branches, for instance, or by virtual method calls or so. And then the pointer relationships might not be clear anymore, and then you have to take into account all of them. Again, points to sets are special cases of value contexts. I will be talking about general value contexts later in this course. If you have a flow sensitive analysis, then you can also use access paths to cover some level of object sensitivity. So if you go back here, I told you that basically this information here, right, about these two allocation sites, it's telling you more about these particular objects here and where they originate from, okay? By looking at the string, we know that this object here was allocated here and that object was allocated there. This is explicitly encoded here in this representation. Now, a different way of going about this would be to simply track the access path in itself. Okay, so not using this representation, but rather tracking a.f.x, which is a access path based analysis then basically, right? And that's also done by many current analyses. And that implicitly can give you similar, at least, information. So you can also use that to track back where these different objects originated from. And that can also give you a certain level of object sensitivity. But I have to say that the exact relationship is still an open research problem. So that's still an interesting publication to be written about how exactly do object sensitive analysis relate to these access path based analysis. Now, there are some interesting empirical papers that show that if you have even just one object sensitivity, it can be extremely effective during call graph construction. Why is that? Well, let's take a look at such a procedure here. So let's assume we have two different, well, potentially different objects here, right? And we call foo on this one object and then foo again on the other. Then here you will see that the call target, right? So the procedure that actually is called here, or the procedure that is called there, it does not actually at all depend so much on the location here, right? So it really depends on what kind of object this foo call is being made on, right? So if these two objects A1 and A2 are of the same type or come from the same allocation site, then they are going to go to the same target procedure. And if not, then they are not, right? And it doesn't really matter what location this call is made at. So distinguishing calling context strings doesn't really make that much sense here, but distinguishing the call sites here that these calls are made on, that matters a lot, right? So they do depend on the type of the receiver object. And that's why object sensitive analysis makes a lot of sense here. Now, unfortunately, the call graphs that you can create with Spark in Suite, they are context and object insensitive. So you don't get that level of precision. Sometimes you can add object sensitivity in a second step. So when you have an analysis that walks the call graph to create an interprocedural control flow graph, you can take that additional information into account and use that to filter your call graph. Another possibility, if you want to use, if you want to create object-sensitive call graphs in the first place, there are extensions to Suite. One in particular is called Paddle. It's a pointer analysis framework based on BDDs, binary decision diagrams. And that was particularly designed to perform object and/or context-sensitive call graph analysis. And you can plug it into Suite. It's not always trivial because it's basically a native library that needs to be compiled for the right architecture you're using. But then if you plug this into Suite, you can create such call graphs as well. That's all I wanted to say about object-sensitive analysis. And yeah, before I conclude this week's presentation, I still quickly want to talk about different flavors of different sensitivities and how they relate to one another. So in particular, we can assume that on this axis here, we have an increasing precision of data flow analysis. And then the most simple analysis you can possibly think of is a flow insensitive intra-procedural analysis. We have seen this in the very beginning of this course. This would basically be a type system, right? So that's really the most simple system you can think of. Now, there are type systems that are inter-procedural. There are even type systems that have some notion of flow sensitivity, but usually when you talk about type systems, they fall into this category. And I would say all static analysis that are implemented that way, they are usually used for type checking. They're usually not good for much else. Then we also have flow sensitive intra-procedural analyses. These we have seen with the monotone framework, right? And they are also used for simple, checking of simple properties within a procedure. So for instance, if you have a compiler or integrated development environment that tells you, oh, you're using an uninitialized variable here, that's something that you would implement through such a flow sensitive but intra-procedural analysis. Then we have seen context insensitive, flow insensitive analyses. These are the ones that are used for pointer analysis, for instance, right? So we've seen Spark. Then there are context insensitive but flow sensitive analyses. But like I showed you, these are typically not such a good choice, right? Because you can have information about all these unrealizable paths, and typically you end up getting something that is not very precise, and often it's even not very efficient because you basically propagate all this senseless information through your program. And actually, fortunately, I have to say, when I look into the scientific literature these days, there are not that many papers anymore that propose such analysis. I have to say, some 10, 15 years ago, that was still the case. When I started as a PhD student, I even myself still published a paper on such an analysis, but that was actually more of a negative result. So that part of the analysis that was context insensitive and flow sensitive didn't really work. It was not scalable, and it was also not very precise. But back then, I didn't know any better, and many people didn't. Then you also have context sensitive, but flow insensitive analysis. And interestingly, empirical studies show that this actually has more potential. So for many programming languages and programs written in these languages, studies have shown that it's more important to care about context sensitivity than it is to care about flow sensitivity. And so when you have an analysis that disregards the program order, so it's flow insensitive, but it nonetheless does take context sensitivity into account, that can actually bring you a long way. And I told you there are such context sensitive but flow insensitive pointer analysis, for instance, as implemented with PEDAL. But there are also other such analysis. For instance, I know that in the DUPE framework, they have also implemented a taint analysis in that style that was actually also shown to be relatively precise. And that was also a very interesting result here. Then, and here I would say this is really sort of the cutting edge of what you can do, are context sensitive and flow sensitive analysis. And these can then also be further optimized for precision. So we will also still be talking more about field sensitive analysis, for instance, and demand driven analysis, which I will be covering in DECA 2. But these then basically resemble the top of what you can do in terms of precision in your data flow analysis. And I'm glad to say that in many cases, they actually get relatively close to a runtime result. Obviously, this all is still undecidable. You still have to do approximations. And you will still also get false positives in your analysis, so false warnings, falsely computed analysis information due to this over approximation. But in many practical cases, we have seen that actually this doesn't matter that much anymore, and your false positive rates can actually grow relatively small. So some frameworks that come to mind here I've already named. So we have Spark and Paddle here, just to give you some examples. I don't really have any good examples anymore for this class of analysis because fortunately it's not very popular anymore. Down here we have current frameworks such as Ideal and also SPDS, which stands for Synchronized Pushdown Systems. Recent work of ours that actually showed dramatic precision and performance boosts in this area. And all of these I will still be talking about in DECA 2 because they're quite involved and we still need to explain some further concepts in order to bring this across to you. When you look into such context-sensitive analysis, like I said earlier, typically people mean caller-sensitive analysis, but like I also showed you, there are other notions such as object sensitivity, and Paddle actually supports both of these notions. This also brings me to the conclusion of this week's lecture. So just to briefly recap, so I showed you that context-sensitive analysis, they can add precision over context-insensitive analysis, and we talked about calling contexts, in particular the call strings approach. What I said is it's nice and that it generically applies to any analysis in the monotone framework, but it has problems with recursion. And you have to find this, K that you can use for K limiting, which is always a pain. Then we also talked about value context for object sensitivity. So what you can see here is that in general, this call strings approach and also related approaches like object sensitivity, they do work, but they have also some problems. And actually, there's also another major drawback of the call strings approach that I still briefly want to talk about because it very nicely motivates what will be coming up in the next week. Let's take one further look at this final example that I want to show you. So let's assume we're doing again some taint analysis, okay? And here we have 3 different taints, let's assume, right? So this is all sensitive information. And it's being assigned to these fields of these different objects here, let's assume, okay? And now I'm calling foo with all of these different objects. And if we take a look at foo, it's basically extracting a value out of the f field of the first parameter and assigning it to the g field of the second parameter, so that in the end, actually all of these 3 guys here will be tainted, okay? But now let's take a look at what the call strings approach will be doing here. So we have 3 different call sites to foo here, right? So this is the first call site C1. And now we have our data flow fact AF, and it's now attached to it. It has this calling context string C1, okay? And now I'm analyzing the procedure under this context C1. And then, this procedure could be very long, right? Here it's pretty short, but let's assume it has 1,000 statements or so, right? Then let's take some time to analyze. And we arrive at this result b.g, still for the same calling context. Now at call site C2, we do the same, right? So now we have a different taint, but it doesn't really matter. It's just a taint. To the analysis, it's all the same. Again, we have a.f tainted here, but we now have a different calling context. And because the context is different, we have to analyze that whole procedure over and over again. What a bummer, right? So this is again taking a long time, but in the end, we arrive at the same result, this time only for a different calling context. Now, in case you're getting tired, you have my sympathy. we're doing this again for the third calling context, right? Exactly the same computation, except that now we have a different calling context. And so you can see that we have the same method analyzed equally 3 times. And this really seems like wasted work, right? And so the idea is now that wouldn't it be nice if there were a way to analyze this procedure just once, right? So we would analyze it here, somehow store a summary that tells us, okay, when I analyze this procedure under a context in which A.F is tainted, I know that in the end, B.G becomes tainted. And when I then analyze it under another context where A.F is tainted again, I can just reuse that summary, right? And I can skip this whole lengthy computation and just tell, okay, now I need to taint B.G. And the same here, right? That is something that we would like to do. And the functional approach that I will talk about next week is something that will give you something along these lines. And for many kinds of analysis, it will actually do exactly that. So yeah, just to recap, so here we had these problems of bounding to size k. I've already talked about this. But on top of that, the coarse rings approach, it also wastes a lot of work when multiple different call sites and calling contexts behave the same with respect to the analysis. And therefore, in the next lecture, I will be talking about the functional approach that actually will help you and also everybody else address this kind of challenge. Thank you for listening. Excuse me. I will see you in the next week, and hopefully everybody is still healthy until then. Bye-bye.